Hi everyone, and thank you for joining. So we have the impression that science unravels the mysteries of the universe, but with every mystery solved, a new mystery emerges. The Big Bang gave us an explanation for the expanding universe, but left the mystery of how it came about. Quantum mechanics accounted for the strange behavior of subatomic particles, but led to the puzzle of its conflict with relativity. Dark energy made sense of an accelerating universe, but led to the mystery of why we have no evidence for it. Is there a danger that we're making a fundamental mistake in imagining science can eradicate mystery? And do we need to think of science differently as a consequence? Do we need to abandon the idea that science has the potential to provide a complete explanation? Should we not expect science to eradicate mystery and instead simply require that its theories work well enough for our current aims and purposes? Or is the ability to overcome mystery essential to the effective operation of science and a core process of thinking responsible for its success? That's the focus of our debate today, and now on to our speakers. Avshalom, who will be joining us as soon as possible. Avshalom Elitzur is a professor of physics at the Institute for Quantum Studies at Chapman University, where he became a household name. Harry Cliff is a particle physicist at the University of Cambridge and works on CERN's Large Hadron Collider. And Claudia de Rham is a theoretical physicist working at the interface of gravity, cosmology, and particle physics, and she's based at Imperial College in London. I'm going to kick us off with a general pitch, which is, are we making a mistake in imagining that science can eradicate mystery? And Harry, I'm going to start with you. What's your perspective on that?
I think it's a bit of a weird take on science, actually. The idea that scientists going around going, oh my God, there's a mystery, I must eradicate it immediately. I mean, that's not really why we do it. So, I mean, as a scientist, at least personally, the reason I'm a scientist is because I take pleasure from the process of figuring out problems and making new discoveries. That's really what I think science is all about. It's a process. It's not an established body of understanding. It's a thing that we do as scientists. It's what Feynman called the pleasure of finding things out. So that's ultimately, why we do what we do. And if there were no mysteries, there would be nothing to do as scientists. So we absolutely thrive on the existence of these mysteries. They're essential to science. And so, the question of, can we eradicate mysteries? Well, I really hope not, actually, because if that happens, then we'll all have to go home, and that would make the world a rather boring place, frankly. But one of the things, if you look at the history of science, actually, we do make progress. So we solve problems, we learn things over time. But as we discover more, the frontier of our ignorance grows. And so, yes, so if we compare what we know now to what we knew 500 years ago, we know a huge amount. Many mysteries have been solved. But I think arguably the universe is more mysterious now than it was 500 years ago, because we're more aware of our ignorance and we're more aware of all the things that we don't understand. So in some ways, kind of strangely, science makes the world more mysterious, not less, at the moment. I mean, maybe in some very far distant future, we will have learned everything that we can learn. But even then, I really doubt that we will have eradicated all mysteries. There are probably, I think, things in science, mysteries that are actually not solvable, even in principle. So, it's quite possible, for example, that we will never understand the very first moments of our universe. They could be hidden from us essentially by the laws of physics themselves. Claudia may disagree with me here. It may be that, say, quantum gravity, the theory that unifies quantum mechanics and gravity, is empirically inaccessible to us, and we will never really know which quantum theory of gravity is right. So there are these kinds of problems that potentially we will never solve. So I think the idea that science is going to eradicate mystery is completely wrong-headed, and that's not actually what we're aiming for at all. We're trying to solve problems and make progress, but I hope the mysteries keep presenting themselves as we go.
Yeah. Claudia, what's your take?
I think it's going to be boring because we're going to understand each other very well. The big mysteries, where's the third one? I'm not sure we're going to solve that one. I think that the key is about eradicating things. I think we are thriving on mysteries, and this is beautiful. And it's the element of mystery, there's almost some element of magic there, and playfulness with nature, which we we're very much thriving on, and I think we agree on this, is not about eliminating them, because then we'd be out of job and that'd be boring. We love the mysteries, and that's what pushes us, drives us to do science and understand them. Then we don't eradicate them. The sort of the mysteries or the beauty in what happens is there. We can explain it. That's not an eradication. It's an embracement of the phenomenon to some level, and that allows us to develop so many more mysteries out of that, which I think is why we're here as human. It's always what has driven us. So we definitely need to keep doing that, and we will. I think in terms of the mysteries we have today, well, let me just say the open questions that we know are present today. What is quantum gravity? What happened at the very beginning of the universe? Was there something before the universe? They are things that I can formulate. I have even, to some extent, the language to formulate some level of those questions. And that is very much the first step. Understanding how to even formulate the question, having the tools, the words, the language to do so is half the battle. And so I'm actually much more optimistic than maybe you are in us as human, in our ability to actually reach to the bottom of that. But there will be other mysteries that will come along the way once we do that. As soon as we understand maybe what happens at the very beginning of a universe, or how to even better formulate their questions, new elements will come along. And we know probably we should have a historian of science coming along, but there's been a little bit of a transition in the way we embrace our knowledge, and we embrace our the way we relate ourselves to physics and to how we model the world around us over the past century, because of the development of general relativity and quantum mechanics, which are very different as compared to what was before. So there would have been, more than 100 years ago, maybe more the sense that we could achieve some definiteness in our understanding of nature, and there was a bottom to it. But already from Einstein's theory of general relativity, the mystery was there from the beginning. And that is quite different in the history of science, in that we didn't need to wait for observations to tell us there's something that don't match our model, there's something that doesn't match the world as described in this model. The model itself, from the outset, told us that it would break down, came with its own mystery. And so we know now from the outset that Einstein's theory of general relativity is not the end of the story. There are mysteries built into that. And we don't need to see that. We have observed black holes, for instance, but we didn't need to wait for the observation of black holes to know that it wouldn't be the end of the story. And I think that's very much the way we understand physics nowadays. We understand that we have models to see the world, to compare the world with, but that's just a model, and the mysteries will remain all around us. Do we have our next speaker?
Yes. Avshalom, welcome. Very good timing.
Thank you. Sorry, I'm late.
So I'm going to throw you right in this, which is to give your perspective on whether we are making a mistake in imagining science can eradicate mystery. Big sigh.
Life without mystery wouldn't be worth living, I think. Mystery is what gives us the motivation to understand the universe. At present, the question is actually not practical. So many things remain mysterious. For a physicist who is aspiring to understand the most basic laws of the universe, still there are too many riddles. Now the question is, will there ever be riddles? You probably remember that Stephen Hawking's book ends with the promise that one day we will have absolute science, we will understand the mind of God, and there will be nothing more to learn, just the details. I don't know whether it will ever be possible, but without doubt, we are very far from that.
I was going to actually, there's something that Claudia said that I thought was worth picking up on. I mean, if you go back to the early 90s, there was a book written by Steven Weinberg, who's a very eminent theoretical physicist, called Dreams of a Final Theory, which is about this idea that you find a final theory of the universe which requires no more explaining. And that was quite popular at the time because I think there'd been a lot of progress in theoretical physics and experimental physics in the 60s, 70s, and 80s. And there was this sense that we were hurtling towards this final point. And I think the lack of progress along that line in the last 30 years, I think people have quite a different view now, that actually this idea that we're almost there it now seems like this final theory, if it is indeed possible, is very far beyond our reach. I don't know if you would agree with that.
And I think Weinberg himself would agree with that.
Yeah.
Before, a few years before he passed away, I was sitting in a conference with him. And that was very much his perspective, much more in terms of effective description and layers of physics. We are in stairway to heaven, if you were, but we're never going to reach heaven. We're always going to keep climbing and climbing. So I don't think there is, and if we were to ask him now, I think he wouldn't think either that there is such a thing as an ultimate level of truth. I think what there is in our inability to even understand what the mysteries of the future will be. But I think nature is always a step ahead of us, so we will continue. I'm sure we will continue.
I mean, when it's described as a stairway to heaven, it suggests that maybe there has been a wrong assumption that science is the process of trying to find absolute answers, as opposed to having this North Star goal, which just keeps motivating us to find out more. It's slight.
Yes, so I think we were discussing about that a little bit before.
Yeah.
I think it depends as well a little bit on what type of science you're doing. And at least we are very much into fundamental science. And so we understand that it's not about having an ultimate truth. The way we understand the world is a very good description of what happens, but at some point something else has to take over. It doesn't mean that our excellent description, we just throw it away and we just replace it. It is excellent for our everyday life, and you all came here without needing to know about the ultimate truth about everything, because that was good enough for us to live the life that we're doing, and it's going to be for most of the time as well. But they are, even now, they are in our understanding of physics beyond the realm, different dual descriptions. And so you can see things in a particular color, or you can see a symmetric version of that use different tools, that use different words, and yet it gives the same predictions, it gives the same type of underlying phenomena, and yet there are different ways to see it. And so what is it we're doing? Are we really trying to look for an ultimate truth? No, we are trying to make connection with nature and trying to see how we can embrace it and understanding the best we can in a way that we can make predictions and then go further in that quest.
Avshalom, do you want to chime in?
Actually, can we even imagine a final theory? Suppose, just let's imagine it, and we will see that it's impossible. Suppose somebody comes and says, you want to know why the constants of the universe are this and not others? Here is the answer. You can't even think about it, because then every child will ask, so why this number and not another? So the sense of mystery will always remain. Think about the Big Bang. We thought that it explains everything. Immediately, once there was the theory of the Big Bang, people asked what has been before that. And then cosmologists said, you can't ask what happened before the Big Bang, because time itself was created at that time. Does that dispel the mystery? I think that it makes it even more mysterious. There is a beautiful book by Dawkins, Unweaving the Rainbow. So Dawkins, who is a very militant atheist, said, look, actually there is nothing mysterious in our universe. Okay, science just shows you how the rainbow is beautiful, but it dispels all the mystery. No, it does not. I am thinking about the way Dawkins tried to explain why our universe obeys such beautiful mathematical laws. And he said, here is an explanation. You know Darwin's theory? Darwin's theory explains life. So you ask about the universe, here it is. Universes give birth to one another, universes die, so you have an evolution of universes. We live in a universe which is rich enough to host life and intelligence. Immediately the question comes, if there is such a universe, if there is such a natural selection of universes, there must be some kind of a hyper universe in which this lawfulness exists. And then the same mystery that we have ever since Plato just comes back to us. How is it that the world is so rational? Or as Einstein said, the most incomprehensible thing about the universe is that it is comprehensible.
Say that again.
The most incomprehensible thing about the universe is that it is comprehensible. That's a miracle. And okay, I know that I sound like a school teacher, but there is a paper that you all want to read, and this is by John Wigner on the miraculous fitness of mathematics to the language of science. And he ends it with, he was also, I believe, an atheist, with a beautiful religious ending. The application, the fitness of mathematics to our universe is a miracle that we don't understand, neither deserve. So at least let's learn to appreciate this gift.
It's always amazing with these debates how quickly they can just expand. And to try and contain it a little, could we assume that the models that we have are there specifically to address certain aims and purposes of our understanding? Harry, I'm going to go to you first.
I mean, I think our theories or our models that we use to describe the universe, they're just an approximate description that matches the current data that we have. I think there's an interesting debate to be had about at what point do we have so much evidence for some phenomena or some concept that we start to think of it as actually being real. So actually I was recently criticized in a review of my book, which I'll be selling in the bookshop afterwards, where I kept talking about, I'm a particle physicist, and I kept talking about the basic building blocks of the universe being quantum fields. These are mathematically these kind of infinite things in space and time that particles are little vibrations in, and we think of them in our theory as being the elementary constituents of the universe. And there's so much evidence for quantum fields, and it's such a great description of all the precise data that we get from a whole range of experiments, that we tend to just talk about them as if they physically exist. And I suppose in the back of everyone's scientist's mind, you're thinking, okay, well, you're aware, yes, this is a model, it's an approximate description, but if you say that all the time, it makes having a conversation very difficult. It's a bit like, this chair, for example. If my internal model of a chair is it has some legs that support it, it's got a flat surface to sit on, I can do an experiment where I sit on it. All I'm actually experiencing are the electrical signals from the nerves in my bum and the photons that hit my eyes and my retinas. But at some point I say, okay, the data matches this concept well enough that I believe the chair is real. So we don't go around, if you went around thinking, oh, is this chair actually real or is it just some conceptual idea, you'd never sit down. And I think it's a bit like that in science, that at some point we accept these ideas as being real, and we kind of imagine them to be real, even though we sort of know, okay, yes, it's possible that maybe there's another way of looking at the same phenomena, which I think is what Claudia was talking about with this idea of dual theories, where you can have two different ways of describing the same data.
Yes, so we're starting to go there, and I think that is very interesting in the way fundamental science is going nowadays, that we have, for some models, very dual, symmetric, and symmetry is part of all of it, which I think is resonating with your question of why I have the ability of seeing the world in such a symmetric way. But in the way we represent the world, we can have a particular picture or something which we wouldn't recognize it as being the same at all, and yet it gives us exactly the same predictions, exactly the same way to understand the world. And that, who is to say which is which? Neither is right, neither is wrong. And we accept that. We're actually quite comfortable with this idea that we're reaching a realm where our ability to even understand how to connect with reality stops making sense, and what we can do is have approximations of everything. So I think there is a sense in which there is a notion of reality we will all agree on, and that can go to the existence of fundamental particle if we want to. But we are reaching a new area in how we connect with nature, in that it is not about having a fundamental truth, per se. It's about having the ability to connect with it and having prediction for what will come out of this description. And if everything that you predict turns out to be realized, turns out to be the way you thought it should be, then who is to say whether that's reality or not? I don't know. I'm not going to say that's reality, but that's as close to reality that we can envision.
So much of scientific process is about asking questions. Maybe science and the study of physics is actually just about coming up with great questions rather than trying to find great answers. Avshalom.
Imagine Newton's apple, falling from the tree. Now imagine one day you have an apple which does not fall from the tree, but remains there on air. And there are many apples like that. At first, we shall all marvel. Look at this. This is an apple which is not falling. Then after a while, we shall get used to it and say, okay, I've seen that, and there are many apples like that. It takes a scientist to tell you that even if there are zillions of such apples who do that and remain just on air and do not fall, there is some mystery in it. Several of the mysteries of the universe are such that they are just as mysterious as an apple remaining in its place rather than not falling, but because they are very common, the non-scientific mind gets used to it, whereas it takes a scientist to say, it doesn't fit with anything else I know. Take consciousness, for example. I'm sure that this is one of the buzzwords that always comes in such discussions, but I had the privilege of giving a talk in this, How the Light Gets In, on September. We see colors. Now, it is not only that we see colors, that the mechanism of seeing colors is within us. We have an experience of colors, and that will remain perhaps forever outside of the scientific understanding. I see blue and red, and you see blue and red, and by all tests, even if we can peer into each other's brain, we will be satisfied that it's the same process. Still, in no language and with no instrument, I can ever make sure I can never roll out the possibility that you experience red as I experience blue, and vice versa. Worse, I can't even know whether you have an experience of colors at all. Perhaps you are just a very good machine, capable of producing the same behavior and the same speech as a human, and you behave like a human. You laugh and cry and love and hate and so on, but you don't have the inner experiences. The inner experience, this what we call consciousness, is a mystery that persists every day, so we get used to it, but it's still a mystery.
So you're actually saying that scientists are more responsible for maintaining mystery?
Good scientists, if they are good scientists, yeah.
Okay. What do we feel about that?
I think it's not scientists, I think it's us human. I think that's what we see in kids, right? They ask themselves questions, they ask themselves the best questions. We're all, if you want, we're all scientists, but we're all human. I think that's what makes us quite special, and that's something very much to be cultivated. It's something very special.
Is it just me that makes the assumption then that scientists have a particular kind of mindset?
No. Unfair. I say the good scientists, they don't have it. They always look for new ways to, just like children, building and destroying and building and destroying. There is a lot of fun in destroying things that you have built and trying to build it from the very beginning.
Harry, as an experimentalist, what's your view?
I mean, I think that's right, and it's being able to look at a situation or a set of phenomena and identifying what's the interesting thing here, what's the little clue, what's the thing that doesn't quite make sense, that then allows you to make progress. So Feynman said, I think quite famously, it's the thing that doesn't fit that's the most interesting. Or there's another phrase from Isaac Asimov, which is the most exciting phrase to hear in science isn't eureka, I found it, but that's funny. And experimentalists, I think, actually the skill is in noticing some little detail that might easily be overlooked. Often it's by exploring that little detail that you open up a new avenue of discovery. And there are some experimentalists historically who are amazingly good at this. So like Ernest Rutherford, for example, who's a hero of mine, who's one of the founders of nuclear physics. He had this amazing ability to look at some experimental result and go, that's the bit that's weird, and we're going to investigate that. And that actually, so the way he discovered, the reason that he discovered the atomic nucleus famously was he and Geiger were doing an experiment where they were firing alpha particles, these particles emitted by radioactive atoms, through a gas-filled tube. And they had a photographic plate at the end, and they expect the alpha particles to just hit a very sharp point. And they were coming out a bit blurry. And you might just think, oh, maybe our instrument's not very good. And Rutherford knows, like, no, there's something really strange happening here. This shouldn't be happening. And that led to a whole series of experiments that then culminated in the realization that the atom isn't this wobbly plum thing that everyone thought it was, but it actually is like, has this tiny nucleus at the center. So it's that ability to kind of notice the little detail. And I think that's particularly in experimental science. I think theorists maybe have a different way of looking at the world, perhaps sometimes slightly grander or kind of bigger picture. Whereas but I don't know, maybe not.
No, it's all about the details. It's all
yeah.
about, but I think it is just in when you see a problem running, rather than running away from it because it's is different, it's scary, it's something you can't identify. It's actually be driven by that. And I think we all have it to some extent. So I don't want to say you are special, of course, but, but scientists are special in some ways, but we all have that. And as theoretical physicists, it is the same. We're trying to have an encompassing way to describing the world, but every single discovery is built out of small details, and putting them together, that's really where it comes in. There's no grandiose plan that you're going to come up with a new theory of everything from the outset and then build your way towards that. You start with small details, and you see from there how to build them up together. So we're all architect in that sense, but building the way from the bottom up rather than the other way around.
But that suggests that the models are established, and what you're saying actually contradicts this idea that the models are standard and set, and the foundation on which you build knowledge.
So exactly, they are very good approximation for what we see, what we're experiencing up to some extent. But for fundamental physics, at the very least, for fundamental science, we very much embrace the idea that they are not absolute by any means, and we know that many of them, they will stop making sense at some point, and we need to push ourselves to go and look for this failure, embrace that failure, embrace the points where it doesn't work out, and build our way from that. It's not something to be afraid of. We're actually looking for those points.
Really?
Yes, absolutely. Yeah. Okay. And that's how we work with experimentalists as well, to look more and more for the points of failure. Yeah. So it is interesting if you look at the last movie, the three-body problem or opportunity. I don't know. I don't know. I don't know if you watch it or not. All of a sudden, physics doesn't make sense, and it's been portrayed as physicists then wanting to stop doing physics because it doesn't make sense, and so the laws we had to describe the world don't make sense. We wouldn't be depressed at all. I would be so thrilled, because there's so many different things to better understand. If something once doesn't fit the box, there's a new piece of the puzzle that doesn't match, that's amazing. We're looking for those things. The reason we keep doing observation and experiments, you may say, we have discovered the Higgs. Why should we go and keep on looking for new physics at the LHC? Why should we be looking for new physics when we have kind of a complete model? It's because we want to look for the point of failure and accept it, and then it is from that we will make new progress, and we will make new discoveries.
I think there's this perception sometimes that scientists are sort of wedded to some established theory and they just defend it against attacks. Now, if you're vaguely sort of visible as a scientist, I'm sure you get a lot of slightly mad emails from people with usually retired electrical engineers saying, I've got a new theory of the universe and gravity doesn't exist. It's all electromagnetic forces between weird particles that I've invented. And they'll send you some PDF with animated GIFs explaining their theory. And they'll say, the scientific community are keeping me down. They're not entertaining my ideas. And the point is, it's not because we are wedded to our understanding of the universe. We're desperate to find places where it breaks down. But you look for the sort of ideas that are promising, where there's some evidence that it's breaking down and there's a new explanation. You have to be skeptical both to your own theory, but also to new ideas that may come along. So you have to be simultaneously sort of self-critical of the ideas you're working with, but also critical of new ideas that emerge, because they have to do better than the current theory. So we basically will hang on to a theory as long as it is the best explanation that we currently have. But as soon as something starts doing a better job, people will be very ready to let it go. I mean, I guess to some extent we're all human, and if you're a theorist, say, who's come up with a standard theory, you might have some emotional attachment to that theory that could be difficult to let go of, and those dynamics, I think, are always there. But ultimately, most people will eventually accept that, okay, as much as I invested my time and energy in this particular model, it's not worked out, and I will move on to something else.
I wonder how easy that transition is, though.
Oh, we are humans.
Yeah, exactly.
Yeah, but I do get the impression that physicists are kind of locked into, an established model, and any deviations from
we
that.
are not.
So there's a healthy inertia, I think. It is inertia, and that is healthy to some extent, because we can't wake up every morning and say, okay, let me reinvent the world and let me start all over again, because we're not going to make progress. There needs to be some level of steps. We need to go through steps, and there is some good enough approximation on which we rely until the point where we realize, okay, that wasn't good enough, and I'm gonna embrace it. So that process can be emotionally painful, we all know, but also it is healthy to have some level of inertia to keep some stability there. But that shouldn't be confused about too much. It doesn't mean that it's absolute, and it doesn't mean that it's fundamentally rigid. So it may need a few generations sometimes, so a generation of scientific generation, not human generation, but it needs the thought process to go through. And also we need to be able to see how it compares with the existing models. The notion of doing better. What does it mean for a theory to do better than another theory? You always need to go back and relate to the world and seeing how many prediction it has. You may imagine that if you have a theory that has no prediction at all, so cannot ever be destroyed, that's a perfect theory. But then it's just in your head. Then it has no connection to reality. If it makes no predictions, you can never test it. Then it doesn't become anything related to science. Then I would say it may be perfect, but it's not science.
Avshalom.
You mentioned inertia. Think about relativity. If there are no black holes, then general relativity is wrong, because all calculations show that when there is enough mass somewhere in the universe, you must have a singularity. Have somebody prove that there are no black holes, that would be a disproof of general relativity. But once black holes exist, they also show that relativity is wrong, because what happens within the black hole is something that relativity cannot tell you. It gets all kinds of infinities. So this is what is so beautiful about science. Every theory just shows you where it ends, where it can no longer answer.
It's limitations.
And it's a limitation, and it is also an invitation for the next theory to come. You know that Einstein's, it's a long story, but Einstein was a good person. He was a nice guy, you know. He was not jealous of people, he was kind to people, but there was one person to him he was not nice, and that was his former teacher of geometry, Hermann Minkowski, who was a great genius. And Hermann Minkowski hated Einstein when he was a student. He called him a lazy dog, because Einstein never showed to the exams, but learned, he never showed to the lectures, but came to the exams, got a good grade, and went on. And he said, that lazy dog never visited my class. One day he heard that lazy dog, Einstein, invented special relativity. He said, I'll show how it works geometrically. And when Einstein heard it for the first time, he said, a mathematician has managed to make my theory incomprehensible, because he was still angry at his teacher for. They met a few times in Göttingen, and we don't know of any letter they exchanged or whether they said good morning to one another. It's still a mystery. But then, tragically, Minkowski, he was 40-something. He got appendicitis and died. And before he died, he said the following. What a pity to die at the dawn of relativity theory. Now, relativity theory, the dawn is long over. It's just up there. But there is always a new dawn, and I wish for every one of you that it always will be a pity for you to die.
I do feel that we are in agreement that everyone is in pursuit of the mystery. We're in pursuit of unanswered questions. That seems to be what's driving all of you. Is that a fair assumption?
Yes. I've been talking so far about physics, but let's think about mathematics. Mathematics, we consider it to be the supreme science where you have the absolute truths. And then the greatest revolution in mathematics was by Gödel, who showed that there always will be, in any theory, there will always be assertions that are true, but you cannot prove them. So you need a wider theory to prove them, but then that wider theory will again have assertions. Gödel's incompleteness theorem is one of the greatest achievements of the human mind that I think, me at least, that we do not really comprehend how deep it is and how fruitful.
Somehow I'm a little bit more skeptic that we are curiosity driven, but deep down we're still looking for applications in some sort or another. And sometimes this application can be a technological application. They can be there tomorrow. I at all way to do that. I'm happy for application to be there in 1,000 years. I'm happy for there to be no practical application in a life, no benefit to me directly other than the beauty of it. But there is some application. It has to be some application in how, again, we use it to connect to the world. So it has to be in such a way that we are able to use it to make predictions and do something with it, as you mentioned, do something better with it. Otherwise, I think it is not science to some level. Otherwise, it's artistic, which has some drive to it as well. But when we do science, there is this level of applicability to how we relate to
Claudia, I feel like
nature.
you've just brought us right back down to earth, because we were kind of, woo.
I think, so the way we justify, say, big experiments like the Large Hadron Collider, you would struggle, I think, to sell it purely on the scientific questions. Like, we want to understand the Higgs boson, for example. You're not going to necessarily give some people 5 billion just to do that. But then there are all these spin-off technology arguments around you develop new types of magnet that allow you to build MRI machines or cancer therapy machines, the World Wide Web, all this kind of stuff gets thrown out there. But I think as physicists, broadly, we're not really motivated. It's nice to know that there are benefits of the research, but as individuals, I think we're mostly motivated by the problem solving. I'm quote Feynman once more, which is one of his most famous quotes, which actually I had at the beginning of my PhD thesis, which is, physics is like sex. Sure, it may give some practical results, but that's not why we do it. But I think the reason we continue to invest in science is because, okay, we allow scientists to play and have fun and discover, and there's a duty on us as scientists, therefore, to share that knowledge beyond just academia. But also it does generate, as you learn more about the world, it kind of invariably produces these applications that are very hard to foresee often, even as the people working at the forefront of a field, but then can quite often, maybe in the very distant future, have a big impact. But it's interesting, we're talking about sort of motivation or mystery. We're all physicists here, and I wonder if you had a biomedical scientist on the panel, whether they would have the same thought about why they do science, because I could imagine in that case it might be you're more motivated by the desire to cure some disease or actually solve a real world problem, whereas we're sort of one step removed, I think, from the practical, even though it may have practical applications.
Yeah, I think we're many steps removed from that.
Yeah.
But it is in our DNA, and I think we have to embrace it. It is in our DNA, and has made us human quite, to some level, now we can debate, quite successful at what we do in following that drive, whether we know why we're doing it or not. But it is part of our DNA. It's an evolution that has allowed us to get here.
Well, I'm a mechanical engineer, and when I visited Snow Lab in Canada, where they do dark matter research, I said, are you not frustrated that you haven't found dark matter yet? And he said, if we ever find it, I will be so upset. And I just, as an engineer, seeing all of that instrumentation and all of the experimentation, I had to sit down and kind of really understand that answer. But, talking to all of you today, I can see that the mystery is actually driving.
But it's not fun if you never solve a mystery, I think. You've got to solve something at some point. You want to solve the mystery and then move on to the next one. I wouldn't want to carry on building dark matter experiments to never find anything. I mean,
really?
No.
Okay.
No, but what's interesting is even when we detect dark matter, which I'm really hoping we will do, then there will be new mysteries out there, and then we'll understand so much more. We'll have this dark sector out there. We'll be able to communicate with it, and all the mysteries this dark sector is going to bring to us. Can you imagine? That's going to be that. I can't wait for it.
Yeah. I mean, I think if it was ever found, it would lead to so many other questions.
Yeah, exactly.
And, it would just open another Pandora's box. So we all seem to be in agreement, which has thrown me slightly because this is meant to be a debate. But I think there's a real agreement that actually keeping the mystery in physics is essential to progress. It keeps us questioning. It keeps us questioning our questions. And long may that be. Thank you so much for listening. And yes, round of applause. My amazing panelists.